Hi everyone, I am Harim and I am presenting my paper titled On the Time-Based Conclusion Stability of Defect Prediction Studies, which was published in EMSE 2020 along with my co-authors from University of Alberta. Empirical software engineering researchers often make claims based on the empirical evidence available at the time of research. However, their claims often go beyond the context evaluated. For example, if you look at the area of defect prediction, will the claims of a defect prediction model hold even after a year? If not, we call the model's performance to be inconsistent with itself across time. Conclusion stability is a desired property of defect prediction models where the model conclusions hold even when the context changes. In this paper, we are going to evaluate how does time affect the conclusion stability of defect prediction models. We have noticed that most of the prior studies have used k-fold cross-validation, which sets aside one release for testing in each fold and trains the model on all the remaining releases. Now one may clearly see that some of the data that is used for the training may come after the test release on a time series, and therefore a cross-validation model surely involves time travel. We also evaluate in our study if time travel leads to an overestimate of performance. In order to evaluate our claims, we have replicated 5 cross-project defect prediction approaches. These approaches were taken from Herbold et al.'s comprehensive benchmarking study that they carried out in 2018. We've also used the same dataset as them, but since this dataset had missing time information, we fetched it from the GitHub. Our evaluation is strictly time aware, and therefore we have proposed TimeAware configurations. The main idea behind these configurations is that we divide the dataset using n split points. All the data before the split point is used for the training, and all the data after the split point is used for the testing part. One may see that using these split points, we have divided the data into 4 buckets, which is just an example. Each bucket represents 12 months long time period, and each bucket has different projects and different releases of different projects. Now, we can choose k number of buckets at a time to generate our training and test data, and this k is actually the window size, referred to as window size in the paper. Look at the example of the first configuration, which is constant. You can see the split point here in the slide in blue color. We use the constant here means that we can use a constant number of buckets for the training part and a constant number of buckets for the testing part, and that constant is actually window size, which is denoted as k in the slide. So when the window size equals 1, we were able to generate our training test pair B1 B3, which means that bucket 1 goes for the training and bucket 3 goes for the testing. Now see that this bucket might have different projects and different releases of that project. We then increase the window size to 2 and 3 and generate more training and test pairs by including 2 buckets for training and 2 for testing, and 3 buckets for training and 3 for testing respectively. If we do not have enough data available at a particular split point, we just use as much data as available, and therefore you see the null here. One should also note that we have not chosen bucket 2 in any of the training and test pairs. That's because we want to leave a gap to avoid any kind of data overlap. Once all the pairs have been generated for this particular split point, we move the split point farther and we generate the training test pairs using all the values of k again. Our next configuration is increasing constant. It is different from constant in the sense that you can only choose a constant number of buckets for the testing part, but all the data that is available before the split point is used for the training. Therefore, when the value of our window is 1, we use just one bucket for the testing, which is B3, but everything before the split point goes for training. So on and so forth for k equals 2 and k equals to 3, where we choose 2 buckets for the testing and 3 buckets for the testing respectively. However, the training data remains same since everything before the split point is used for training. Constant increasing is our third configuration, and it is just opposite of the previous one. We use a constant number of buckets for the training, but everything after the split point is used for the testing of the model. Increasing it is our last configuration, and in this configuration we take everything that is available before the split point for training, and all the data that comes after the split point goes for the testing. In this way, we were able to generate about 18,000 training and test pairs, and we generated 18,000 models for each approach. In this figure, I'm just showing one particular approach and all of its 4 configurations. The F score is represented on the y-axis, whereas the time is on the x-axis. The green line that you see on this in this graph is the result of the replication study of the Herbold et al. Study that we did with the dataset at hand. Now one may see that as you move across the timeline, the f-scores vary drastically, and it is very different from the 0.4 value that this green line represents. Our original hypothesis was that a technique has stable conclusions if the standard deviation of a particular performance measure is less than 0.05. The standard deviation of f-scores, MCC, and G-measure in our results is 0.05 or higher. We just do not see a lot of variation for AUCs though. We also compared the results of cross-validation methodology of Herbold et al. With our TimeAware evaluation, and according to the results of Wilcoxon rank-sum test, there is a statistically significant difference between TimeAware and time-agnostic results. However, the cliff delta sizes were small to negligible. Here we show how the ranks of our TimeAware, how the ranks of different approaches vary in our TimeAware experiment. This is, however, just one approach and one window size for a particular approach. One can see that the ranking of each approach varies as you move across the timeline. So we have seen that although the benchmarking study of Herbold ranked NAM as the top approach, but our evaluation shows that the rank of all approaches vary at different split points in time, and all approaches except NAM 15 have inconclusive ranks. In summary, there is a general lack of conclusion stability in the area of defect prediction. We have proposed a time-aware evaluation methodology and evaluated 5 different approaches across time. We conclude that models hold different conclusions over different periods of time. Therefore, researchers should couch their claims of performance within the context of evaluation. Moreover, cross-validation is not a correct evaluation methodology and a time-aware evaluation should rather be conducted. Thank you.
Hi everyone, this is the second QA session of Defect prediction, data issue, and bug classification. We have with us the first author of the paper One-Time-Based Conclusion Stability of Cross-Project Defect Prediction Models, Arim Sahar. Welcome, Arim. Please feel free to write your question in the chat. I can see so far still nothing to come up. I have a few questions, but first of all, I'd like Harim to introduce herself and tell us a bit more about you. Okay. The audio seems to be a bit low. Do you mind to increase the volume of your microphone? I don't know if it's just for me or for also. Yeah. Okay. It's also for the audience. We can hear you. I can hear you, but it's very, very low. So if you can, please try to raise the volume. Yeah, speak louder, get closer to the microphone. Yeah. A bit better for me. Well, I can still understand you. Can the audience please text if they can hear now? Otherwise, we can text.
I can try without the microphone.
Now it's better. No, now it's better. So just keep it close. Okay, very interesting. Very interesting work. I do research in the same field, and I really enjoyed reading the paper. I have a pretty technical question on the evaluation part. I was curious to understand how you set the threshold for the standard deviation for the stability of the model. When you evaluate if the results are stable, you set a threshold of 0.5 to compare on the standard deviation. Where this comes from? Have you tried several thresholds, or does any rationale for the 0.5? I like the analysis you did. I'm just curious of these details, basically.
Their paper that a 5% threshold in a performance metric is a significant difference.
Okay.
So when you consider 5% as an absolute value for a performance measure that ranges from 0 to 1.0, 0.05 is so.
Okay.
Yeah, and then there's another paper from the Queen's lab by Dr. Nen, I guess. Dr. Nen. Yeah, that's her name.
Don't worry.
She also says
Okay. I think the audience might still have a difficulty to hear you because I really making an effort to do that. But I repeat your answer so that everybody can hear.
Is that better without the microphone now?
Yeah, now it works.
Okay, yeah, I guess my headphone isn't good enough.
No problem. So if you don't mind to repeat your answer.
Yeah. So
that'd be great, because now it's working.
in the in one of the papers by Herbold et al., who we compare with, they said that a 5% performance threshold is significant. And another paper by one of the profs in Queen's Lab, they say that a 2% is also significant. So based on those two papers, we set our threshold to 0.05 because 0.05 and 0.1 because an absolute value of 0.05 and 0.1 is more than 5% and 2%, which was used in the literature previously.
Okay, thanks. And I understand that you have experimented with cross-project defect prediction. Do you expect same conclusions to hold with just-in-time defect prediction or with inversion defect prediction?
We expect that in case of within project defect prediction, the differences would be more obvious, which means that within project defect prediction is more likely to be affected by not using data in order of time. But we did not just evaluate ourselves in our study. We just compared cross-project defect prediction models. But there is a recent paper that I guess is presented in this session, which is on within project defect prediction, and that talks about time as well.
Yeah, there have been a few papers published in the last 2-3 years about how careful we should be when we build these models, because previous literature, including myself, at times we have forgot about the chronological order of these items and done something that it's invisible in practice. And actually, at FSC 2019, we have published a paper coming to the same conclusion you came, but for software vulnerabilities. So when software vulnerabilities prediction studies suffer the same problem, basically, when you do ignore the chronological order of the observation, you get much better results, very optimistic results, as soon as you introduce the chronological order, which is how would you use a model in practice. The results drop dramatically to an extent that the models were useless, basically.
Yeah.
So I think it's pretty good that as a community we're looking towards this problem, making our evaluation closer to the reality. So I really appreciated your work in this respect.
It's your paper. I would like to see that later.
Yeah, I'll share. It's FSC 2019. We use different terminology from yours, but I think we're saying the same message, sharing the same message across. We call it realistic labeling rather than ideal one.
Okay.
But I like the terminology you use. It's pretty straightforward as well. Okay, we still have like a couple of minutes left. I would encourage the audience to ask questions, if any. Otherwise, I don't know if you would like to add something. I don't know about your current research, if there's any follow-up on this paper, if there are any other takeaway message you want to share with us.
Not really, except that I came to come across the other paper that was being discussed just before mine, I guess by Tim Menzies.
Yes.
Which also somewhat similar in the sense that they talk about how data varies over, as the project matures, and how the density of defects can vary. So since that happens over time, that also affects our results. That was one of the questions by the reviewers of ICSI, that why do we think that time affects the conclusions? So I guess this paper, as well as the paper by Tim Menzies,